Okay, so in this section, we're going to start really our last unit on topics in the course. And we are going to work with a process called anti-differentiation. So, you know, in math, we always tend to learn something and then we tend to learn the same thing backwards. So we learn how to add, then we learn how to subtract. We learn how to multiply polynomials together, and then we learn how to factor them. In calculus, we learned how to find the derivatives of functions. So now we're going to do that backwards. So we're going to be given the derivative of a function and want to find the original function that has that derivative. And that process is called anti-differentiation, or more commonly, integration. So I want to show you with this first supposition here what we're trying to do. So I have that derivative listed there as the derivative of some function f is equal to 5. And I want you to come up with the function whose derivative would be 5. So try to think of a function that if you took the derivative of it, you would get 5 for an answer. So one of the most common answers is to say that f of x is equal to 5x, because the derivative of 5x is equal to 5. But try to think of another one. So if I think of another function that would have that derivative, I could say that f of x is equal to 5x plus 8. Think about what the derivative of 5x plus 8 would be. The derivative of 5x would be 5, and the derivative of 8 is 0. So that means that's a second function whose derivative is equal to 5. So if I try to do one more, I could say f of x is equal to 5x plus 25. That would also be a function whose derivative is equal to 5. So you kind of get the idea that the part that gives me the 5 is that term 5x. But if I add any constant onto that term 5x, I'll have a totally different function, but I will still have a derivative of 5. So when I do anti-differentiation, or when I do integration, you actually come up with a family of functions as opposed to a single function, because there will always be this constant that I can add onto the function that I make up, or that I come up with, that will still have an equivalent derivative. So what we would say is the family of functions that has this derivative 5 would be 5x plus some unknown constant, which we represent with a c. So all of our answers when we're doing our anti-differentiation in this section is going to have that plus c at the end of our answer. So that function that we come up with is known as the antiderivative. Now, a couple of notations, because we're not going to say find f of x if the derivative is. We have a symbol for that. So if we go over the notation for integration, the first thing is the integral symbol. And that integral symbol is just, looks like this. Looks like kind of an S that didn't make it all the way through. So there's my integral symbol. And then what I put behind that integral, what I am going to take the integral of, is called the integrand. So in that problem earlier, what I would have wrote, instead of saying, suppose the derivative is 5, find f, in notation form it would have looked like this. I would have said the integral, so I use my integral symbol. And so there's my integrand, which is the derivative I wanted you to consider. And then the dx after it, this notation here, is basically saying with respect to the variable x. So it's telling you kind of what variable to use in the function that you write. We're only dealing with single variable calculus, so we're not, this notation right here isn't going to be as meaningful to us as when you have more than one variable involved in the integrand, but it's still part of the notation that you want to get used to writing whenever you're writing an integral. And then what we set that equal to was that family of functions, 5x plus c. So there's my antiderivative, and then my c is known as the constant of integration. That's that extra value, that extra constant that I could add on to create my whole family of antiderivatives. Okay, so there are rules, just like we had derivative rules, there are integration rules that we need to know so that we can, instead of just trying to think in our head what is that function that has that derivative, we have rules that we can follow. So there are 4 rules that we need. So let's go through those rules real quick here, and then we'll do some examples. So the first rule is the rule basically that we used in that first example with 5, and that's the constant rule. So the constant rule says that anytime I integrate a constant, the way that I come up with my antiderivative is that I am going to put the variable right after the constant and then add my constant of integration. So over to the side here, I've got some just real quick examples of each one of these rules. So if I wanted to integrate 2 with respect to x, my answer would be to take that constant 2 and multiply it by my variable x and then my plus c. So the integral of 2 dx is 2x plus c. Now, the power rule, the second rule that we're going to look at, is probably the rule that you're going to use more often than any other one. So this is what we do when we're looking at a term that has a coefficient, a variable, and an exponent. So something like x to the 8th. I'll work through that example with this rule. So the rule says if I have a term that's written as a coefficient, which in this case my coefficient is 1, my variable and my exponent, the way that I integrate that is the first thing I'm going to do is create my new coefficient. And my new coefficient is going to be the old coefficient, which is 1, over n plus 1, where n was the old exponent. And then the new exponent on my variable is going to be the old exponent plus 1. So this should kind of make sense to you, because if you think about, we're doing the opposite of doing a derivative. When we do a derivative, we're constantly subtracting 1 from our exponent. So if we're going backwards, we're putting that 1 we subtracted back in. So let's look at this very simple example over here of the integral of x to the 8th. What I'm going to do is take the coefficient that's there on my x, which is 1. I'm going to divide by the exponent plus 1. So 8 plus 1 would give me 9. So 1 over 9 is my new coefficient, then my variable, and then the exponent will be the old exponent plus 1. So what you divide by here is going to match what my new exponent is. And then don't forget, I need my constant of integration, so I'm going to add my c to that. Okay, now the next 2 rules are kind of specific. The logarithmic rule is a very, very specific rule that's only used in the case of x being in the denominator and x being to the first power. So this rule here for the logarithmic rule is specific to something over x to the first power. It's not for every term where I have x in the denominator. If I have 1 over x squared, for example, I do not use this rule. It's only if I have x to the first power in the denominator. And what that rule is that is a very specific rule. The integral of a constant over x to the first is the natural log of the absolute value of x. And remember, we're putting that absolute value there because I cannot take the logarithm of a negative value. So that's forcing that value to be a positive value. So if we look at why this needs this specific rule, consider this over here where I've got x to the negative first. So I need this rule because what would happen if I tried the power rule on that? If I tried the power rule on this, which would say to take the coefficient over the exponent plus 1, notice what my new coefficient would be if I use the power rule. I would have 1 over 0, which is not allowed. I can't have 0 in the denominator of a fraction. So that's why specifically for, remember, x to the negative 1 is just 1 over x. Move that x to the denominator. That's why this one specific case needs its own rule. So the integral of x to the negative 1, or the integral of 1 over x, is going to be the natural log of the absolute value of x, and then my plus c. Okay, and the final rule is the exponential rule, where specifically I have e to a monomial term. And the way that that rule works, so I've got e to something like 5x or 10x or 15x. The way that that rule works is that my new coefficient on my answer is going to be the old coefficient on e divided by the coefficient of the exponent. And then the e is just going to get repeated. So there's no change to the exponent on my e when I integrate it. So for example, over here, if I want to integrate e to the 5x, that's going to be the coefficient of e, which in this case is 1, divided by the coefficient in the exponent. So that would be 5. And then the e just gets repeated, e to the 5x. And then I still have my plus c. Okay, so let's put all of these rules together and take a look at some examples. Now, if you remember when we first learned derivative rules, we always talked about having to rewrite the problem, the function, in what I called polynomial form, which means that I need each one of my terms to be written as a coefficient, variable, and power. I'm going to need that again for integration. So if I see any x's in the denominator, they're going to get moved to the numerator with the exception of x to the first power. If I see any roots, I'm going to pull them out of roots by using fractional powers. I'm going to do all of that before I start integrating. Now, in this first example, number 5 here, notice that every one of my terms are written in that form. They all have a coefficient, a variable, and a power. I don't have any x's in denominators, don't have any roots. So I'm ready to integrate this particular function. So I'm just going to follow my rule for each one of those terms in that polynomial. So first one, first term, this is my power rule. So the power rule says, take the coefficients that's there, divide by the exponent plus 1. So 3 plus 1 is 4. And then my new exponent is the old exponent plus 1, so that'll be x to the 4th. Now I just move to the second term, 6x squared, and I do the same thing. So this time I'm going to take the old coefficient, which is 6, divide by the exponent plus 1. And the exponent plus 1 this time is 3. And the new exponent on my x will be the old exponent plus 3. So coefficient over exponent plus 1, and then x raised to the exponent plus 1. For the next term, for this third term here, I want to follow that same mantra. I want coefficient over exponent plus 1. So my old exponent is 1, so 1 plus 1 is 2. And then my old exponent plus 1 for my new exponent. And then finally the last term, 2, that's my constant rule, where all I do is attach an x. So the integral of 2 is just 2x, and then you don't want to forget the plus c that goes on the end. Now I'm going to want to clean up my answer a little bit. I've got some coefficients that can be cleaned up. And I've got, sorry, I think I lost my screen there. Sorry. So I've got some coefficients that I can clean up. And sometimes you'll have negative exponents to get rid of. So let me just clean this up a little bit. The 1/4 is fine, so I've got 1/4 x to the 4th. But notice here, 6 divided by 3 for my coefficient. I can go ahead and divide that out as 2x cubed. 5 halves, there's not much I can do with. I do not want mixed numbers. So it was really just that one coefficient, the 6/3, that I wanted to rewrite. Okay, moving to number 6. Let's take a look at that example. Now notice there that that first term, that 4 over x cubed, I want to rewrite that term because I want all of my x's in the numerator, but I do not want to rewrite that one because remember, if I have x to the first power in the denominator, that has its own special rule. So the first thing that I'm going to do is rewrite this. If I have one term that needs to be rewritten, I want to rewrite it all. Don't start integrating until every single term is ready to be integrated. So I'm going to rewrite that term as 4x to the -3rd. Because remember, I want coefficient, variable, power. So moving the x to the numerator next to the 4 changes the sign of that exponent. Then my second term is already in the form that I want it to be in, so I'm not going to do anything. And my last term is in a form that I want it to be in, so I'm not going to do anything. So now I can start integrating. Even though there was only that one term that needed to be changed, I don't want to mix up changing some of them and integrating some of them. Don't integrate until they're all ready to be integrated. Okay, so now we'll go through the process. So for this first term here, I'm going to take the coefficient over the exponent plus 1. So be careful with your negatives. Exponent plus 1, that's going to make that 4 over -2. And my new exponent would be -2. Remember, what you divide by is what your new exponent is. So once you figure out what you're dividing by, just remember that that's going to be your exponent on your x. If we move to the second term, I've got minus the coefficient over the exponent plus 1, exponent plus 1 on the x. And then for this last term, 8 over x, when I've got x to the first in the denominator, that's the ln rule. So I'm going to have plus. Now notice my numerator this time is 8, so that becomes the coefficient of the ln. So this is going to be 8 ln absolute value of x, and I'm running out of room, so I'm going to stick my little plus c down there at the bottom. Now I want to clean this up a little bit. I want to rewrite coefficients in simplified form, and I want all of my exponents to be positive. So if we rewrite this on this first term here, 4 divided by -2 is -2, but remember I'm going to drop that x to the denominator so that I can make its exponent positive. On the second term, I can reduce 2 over 6 to 1 over 3. And then my ln is fine, my 8 ln absolute value of x, and then my plus c. Okay, let's take a look at another example. We've got 2 more examples, and we'll look at one little quick application. So if you want, pause the video and try these 2 examples, and then come back to the video and see how you did. Okay, for number 7, I do have some rewriting to do because I've got that square root in that second term. So I want to pull that x out of the square root position. So I'm going to rewrite my whole integrand. X squared is fine. I don't want to change that. But I've got my coefficient of 3/2, and then I want x to a power. Instead of having a square root symbol, we know that that exponent that matches square root is 1/2. And I want to integrate that with respect to x. So if I do that, now I'm just going to work through the power rule for both of these. So for the first term here, coefficient is 1, exponent plus 1 is 3, exponent plus 1 is 3. Now the next one's a fraction, so it's going to be ugly at first, but we can fix it. My coefficient right now is 3/2. So remember, we do coefficient over exponent plus 1. So I'm going to write my coefficient here over, now exponent plus 1. So remember, 1/2 plus 1 would be 3/2. So I've got my my coefficient is 3/2, and I'm dividing by the exponent plus 1, which is also 3/2. And what I divide by becomes my new exponent, so it's x to the 3/2, and then don't forget your plus c. So I can clean up that second coefficient and have my answer as 1/3 x cubed. Now the nice thing is, even though these are fractions, anything divided by itself is equal to 1. So my coefficient is 1, -1, x to the 3/2, and then plus c. So that's what my final antiderivative would be. Okay, one more. This time we've got x's in the denominator. So any of the x's that don't have a coefficient of 1 need to move to the numerator. So I've got some changing to do, so I'm going to rewrite this integral. 5 over x is going to stay the same because remember, x to the first power in the denominator has its own rule. But on the second term, I'm going to move that x squared up next to the 3. So I'm going to have 3x to the -2nd. And then on the third term, I want to move that x up next to the 6, which means that it has to come out of the square root to be 1/2. And then moving it up to the numerator makes it -1/2. So that's what I want to integrate. So let's go through the rules. For the first one, where I've got x in the denominator, that's my ln rule. So it's going to be my numerator, my ln, and my absolute value of x. And on the other 2 terms, I'm just going to use the power rule. So on the second term, it's going to be coefficient over exponent plus 1. So remember, negative 2 plus 1 would be negative 1, x to the negative 1, plus coefficient over exponent plus 1. So negative 1/2 plus 1 would be positive 1/2. And that would also be my new power. And then my plus c. Now, if we simplify this a little bit, we've got a couple coefficients to clean up and one negative exponent to move. So my first term is fine, 5 times the natural log of x. And now let's clean up this coefficient here. We can divide that and get a positive 3. And then we also want to move that x to the denominator. So this is going to be 3 over x. And then for the third term, where we've got 6 divided by a half, remember 6 divided by a half means 6 times 2. So my coefficient on that last term is 12, and x to the 1/2 plus c. And if you want to take that x to the 1/2 and go back to root form, you can. Just like with derivatives, I don't want any negative exponents. I don't mind fractional powers though. So this would be what my final answer would look like. Okay, one last quick example here of kind of a similar problem, or a familiar problem, I should say, that you've had before. We always, every time we learned a derivative rule, we always did writing the equation of a tangent line. Well, this is that question backwards. So this time I'm not looking for the tangent line's equation. I'm given the slope of the tangent line, and I want to find out the function that it's tangent to. So we're working this a little bit backwards. So remember what things mean again. So we know that, well, sorry about that. We know that the tangent line has this slope. So remember, slope is a derivative. So what we've been told by being told that the slope is 5 minus 4x, we're being told that the derivative of the function is 5 minus 4x. And we want to go back to what the actual function is. So if I want to move from a derivative back to a function, that's what integration is. So to set up my problem, what I'm looking to do is to find the integral of 5 minus 4x with respect to that variable x. So let's integrate this and see what we get. So what I get when I integrate this is going to be my function. So I integrate 5, that's my constant rule, which means I just attach an x. And when I integrate the second term, that's my power rule, where I take the coefficient over the exponent plus 1, and then exponent plus 1 on my variable, and then my plus c. So I'm going to rewrite that real quick, getting that second coefficient simplified. So here's my function so far, 5x minus 2x squared plus c. Now I want to be more specific than that because I was given more specific information. I was given the fact that I'm passing through that particular 0.17. So that means that I have an x value and a y value that I can use to figure out a very specific constant. So now what I want to do is plug the 1 and the 7 in. So my y value is 7, my x value is 1, and that should be enough information for me to figure out that c. So if I do that arithmetic over here, 5 minus 2 is 3. which gives me c equal to 4. So if I put that 4 back into my generic family of antiderivatives, I get a specific function of 5x minus 2x squared plus 4. And it's out of order. If you want to rewrite it in descending order, that's perfectly fine. If you leave it like this, I'm okay too. So there's my function whose tangent line with this slope passes through my function at that particular point. So practice these. They take a little bit getting used to because you're used to going in the other direction. And if you have any questions, let me know.